Hello, chemistry students. Hope you've had a great day today. Hope you had a good lunch and looking forward to teaching you this lesson today. I'm sure the test may have been a little bit challenging for you. I'm looking forward to grading that when I get back. Also, looking forward to talking with you about your rough drafts with your research papers. And we'll talk about a couple things, hopefully, that can improve some of those. But I'm sure you guys will want those returned to as quickly as possible. So I'm trying to finish those up on my travels back to Goldsboro, and hopefully I can get those to you as soon as possible. But today we're going to start a new chapter, chapter 8 today. The entire chapter is talking about chemical compositions and reactions. So this is the very first chemistry class, or chapter I should say, that we really start to talk about how everything works together. Previous to this lesson, we've talked about molecular shapes, we've talked about the Lewis dot structure, we've talked about intermolecular forces, we've talked about a lot of different things, but we really haven't talked about what happens when an element or an atom or a molecule or a compound, when they react with each other. Like, what kind of predictions can we make from that? So this chapter is actually extremely important because it's going to lay some foundations for the following chapters. So it's really, really important. And there's some basic application in this chapter. We're going to talk about some of that today, but it's not extremely difficult, but it's important to be able to do in order to name the molecules, and we'll have to do that later on, and to predict what will happen, what outcome will happen when certain molecules react with one another. So go ahead and open your ebooks to page number 190. That's where we're going to start, page 190. And we're going to start section A. Section A is entitled Oxidation Numbers and Formulas. So we're going to talk about oxidation numbers. We're going to talk about how they relate to formulas and see how everything works together. All right, so make sure you're taking some good notes here because there's some very important rules that you need to get down in order to be successful. If you get these rules down and you can understand them, you're going to do fantastic on this particular chapter. So first, we're going to talk about oxidation numbers. What is an oxidation number? On chemistry, it's much more than just studying elements. It's studying how they react, how they combine, maybe how much energy they release or how much energy they absorb. There's tons of different things to talk about. But one of the things that we have to lay a foundation for is how do we know they actually join together? Like, there's certain elements that won't combine with other elements. And there's a reason for that. There's a reason in their molecular structure. Now, we don't get into that perspective of it. Really, all we're going to be focusing on is, hey, will this combine with this? And if so, how many atoms of each element do I need? And that's where these oxidation numbers come into play. So it's actually very, very important in order to understand how molecules actually can combine. So you can see here on the slide, oxidation numbers keep track of electrons involved in bonding. Remember, when an element bonds to another element, the only thing that interacts is the electrons. The nucleus of each atom is still separate. So the protons and the neutrons are not affected. And this is what we talked about last chapter with the valence shell electron pair repulsion theory, all that stuff with the molecular bond theory, what allows them to bond. The electrons are what are involved. So the oxidation numbers refer or apply to the electrons. They represent the number of electrons that an atom in a compound must gain or lose to return to its neutral state. So again, it won't still be in a lower stable state, and it's going to either lose electrons or gain electrons. And we've already talked about this in the bonding process, but oxidation numbers actually play into that greatly. All right, so we're going to talk about several rules here. These start on page 190 on your ebook, but you can see them up here on the screen. Feel free to take screenshots of what you see on the slide, or make sure you highlight it in the ebook or writing it down. You got to know these rules, okay? Very important. The first rule, a free element rule. The oxidation number of an atom in their neutral form and of atoms in pure elements is 0. So if I just were to, write an element up here on the screen, maybe like zinc, Zn, and I left it by itself, it wasn't bonded to anything. So you didn't have something like zinc chloride. You don't have that. It's just zinc by itself. If I ever ask you what the oxidation number is of a pure element, it's always 0. The oxidation number of a pure element is always 0. Make sure you know that. Rule number 2, the ion rule. The oxidation number of a monatomic ion is equal to the charge of the ion. So let's say I were to write something like, chlorine, and it had a 2 negative charge. Well, you guys can see that the ion here, this particular ion, is an anion because it has a negative charge. Since it's just an individual element, one element, hence the term monatomic. Monatomic means one element. Its oxidation number is equal to the charge. So since this has a -2 charge, the oxidation number is -2. Those are the first 2 rules that you see on page 190. Again, the oxidation number of a free element, an element all by itself, is 0. The oxidation number of an ion, a monatomic ion, is always equal to the charge of the ion. Rule number 3, this is on the top of page 191. Rule 3 is the zero-sum rule. Now, in my opinion, this is probably the most important rule because you're going to have to figure out, again, can these atoms combine? And if they do, how many of each one do you need? That's where Rule 3, the zero-sum rule, comes into play. The sum of the oxidation numbers of all the atoms in a compound must be 0. So we'll talk about this in just a moment. But let's say I have the element sodium and I'm bonding it to chlorine. Well, you'll know this in just a moment, but sodium has an oxidation number of +1. Chlorine has an oxidation number of -1. So obviously 1 minus 1 is 0. The sum has to be 0. There is an exception to the rule, and I'll talk about that in just a moment. It's not a hard exception. It's actually a whole other rule. But this is a very important rule. If I had 3 elements listed here, they would have to, the sum of the oxidation numbers would have to equal 0. So we're going to come back to this rule quite a bit. So make sure you know this rule. Compounds are not electrically charged, so there's no charge in a particular compound. So you don't need to worry about that. Rule number 4, specific oxidation number rules. Now, we have groups of elements that we know the oxidation numbers for all the time, and these are what are listed on the screen at the moment. You have the alkali metals, that is group 1 or column 1. They always have an oxidation number of +1. Always have an oxidation number of +1. That's why in that previous example with the sodium, the Na, when I had NaCl, I knew sodium was +1 because sodium is an alkali metal. So that's why I knew it was +1. So that's the specific oxidation number. Look at the next one, alkaline earth metals, group 2. That's column 2. All of those elements have an oxidation number of +2. So they'll always have that. Hydrogen is +1. The only exception is when hydrogen is bonded to a metal. If hydrogen is bonded to a metal, then its oxidation number is going to be -1. Remember what oxidation numbers refer to. The tendency for what elements do when they bond to something. The alkaline metals and the alkaline earth metals, if you guys can recall, this is another way to remember it because we've already talked about this. The alkaline metals have 1 valence electron. We've already talked about that. Also, we know the alkaline earth metals have 2 valence electrons. We've already talked about that. So when they bond to a more electronegative element, they're going to lose their electrons. So it's not going to have 1 valence electron. It's going to transfer it completely. And we've already talked about that. With hydrogen, it all depends on what it bonds to. Hydrogen is more electronegative than all of the metals, but hydrogen is less electronegative than the vast majority of nonmetals. For the sake of this textbook, we're going to say the oxidation number for all nonmetals is greater than that of hydrogen. So hydrogen electronegativity is greater than all the metals. Hydrogen's electronegativity is less than all the nonmetals. That's why when it bonds to a metal, its oxidation number is -1. That actually has a special term. When hydrogen bonds to a metal, it's called a metallic hydride. That's a definition that you want to know. All it is hydrogen bonded to a metal. So if I give you a metal like copper, in hydrogen bonds to it. That would be an example of metallic hydride. So again, alkaline metals, group 1, have positive 1 oxidation number. The alkaline earth metals have a positive 2. Hydrogen has a positive 1 unless it's bonded to a metal, and then it would have a negative 1 oxidation number. Oxygen, excuse me, oxygen is another one you need to memorize. It has an oxidation number of negative 2. There is one exception to this. It's when it bonds to fluorine, and it would make sense because if it bonds to fluorine, it's got to be a positive oxidation number because fluorine is the most electronegative element. So fluorine is going to be more electronegative, so oxygen would have to be less electronegative, which would make it have a positive. The lesser electronegative element always has the positive oxidation number. The more electronegative element always has the negative oxidation number. There is an exception, and you need to memorize this exception. It's mentioned at the bottom, page 191. It's where you have the O2 2 negative. Okay, this is called a peroxide ion. The oxidation number of oxygen, if it's a peroxide ion, the O2 2 negative, it's going to be negative 1. That's just an exception to the oxygen rule, but it's an exception that you have to know. Peroxide, you're familiar with this, hydrogen peroxide. You see a picture of a bottle of it in the textbook. We know hydrogen peroxide is often used to clean out wounds and different things like that. The way it actually works, it's pretty cool. Hydrogen peroxide is H2O2. So when you mix that or pour it on a wound or a cut or something, it releases one of those hydrogens. It releases one of the oxygens. That's where the bubbles come from. And when you do that, if you lose one of the oxygens, it's going to end up being H2O. So that's also, by the way, why all hydrogen peroxide bottles, if you ever look at them in the Walmart or in the pharmacy or something, they're always a black or a dark brown color. And the reason for that is they cannot allow any light into the hydrogen peroxide, because if light shines on the hydrogen peroxide, that actually gives it enough energy to change into water. So it's actually, you could buy hydrogen peroxide from the drugstore and it end up being just water. Now, usually doesn't happen because of the bottle, but that actually can happen. So in case you're wondering, FYI, that's why rubbing alcohol has a clear bottle, because it doesn't react with the light, but hydrogen peroxide will. Kind of interesting. All right, the next rule you got to remember are the halogens. Halogens are, remember from our electronegativity conversation, they're always highly electronegative, meaning they're always going to want to gain electrons. So halogens typically will always have a negative 1 oxidation number. So halogens have a negative 1 oxidation number. Now, if they happen to bond to a more electronegative element, they would have a positive. But the rule at the very bottom of the screen here that I'm circling, fluorine is always negative 1. And again, the reason fluorine is always negative 1 because it's always the highest electron negativity, and the higher elements with electron negativities are going to have the negative oxidation numbers. Finding oxidation numbers, if one rule contradicts another rule, the rule listed first would be followed. For binary ionic compounds, binary means 2, ionic means it's a metal and a nonmetal. The crisscross method can be used in order to figure out how many numbers, or what's the oxidation number. And we're going to talk about some specific things in a little bit. And then we use the absolute value of the oxidation number of an ion as the subscript for the element of the other. This will make sense in just a moment because I'm going to work an example. Here's an example. Barium and iodine. Okay, let's say barium and iodine, we're wanting to combine them. Barium is Ba, and it has an oxidation number of positive 1. The reason I know that is because it's in column 1. So the alkaline metals always have an oxidation number of positive 1. It's an alkaline earth metal, so it has an oxidation number of positive 2. Iodine, however, is a halogen. So the halogens have an oxidation number of negative 1. You may be asking yourself, where did we get the positive 2? Where did we get positive 2? And where did we get negative 1? Again, that goes back to our rules. If you refer back to your rules, you'll notice that the alkaline earth metals, column 2, if you find your periodic table elements, barium is in column 2. It will have an oxidation number of positive 2. Iodine is in column 17 or column 7A, and it has an oxidation number of -1. All the halogens have an oxidation number of -1. So the question that scientists, chemists want to know is, well, can barium and iodine combine? Well, this is where the crisscross method works, because if I draw a line or an arrow going toward the iodine, and I draw an arrow going back toward barium, then that's going to tell you the subscript on those particular elements. So barium 1, iodine 2 is how barium and iodine are going to combine. Now what's fascinating is this is the only way. This is just an amazing component in a testament of God's order and design, because barium and iodine can only combine this way. You cannot have 2 barium and 3 iodine. It doesn't work that way. And it's just a fascinating way to see the handiwork of God in something as subatomic as molecules. We're talking about a barium molecule or an atom and an iodine atom, but they have a certain way they have to fit together, and it's actually based on their oxidation numbers. It's such an amazing concept, but very simple concept. You could apply this to a lot of different things. It's really not that difficult, but I'll make one up. You can put it on the screen here. Let's say I gave you guys lithium. Let me change this here. Lithium and oxygen. And I wanted to say, if lithium and oxygen combine, what would their combination be? What's the only way they could fit together? Well, lithium is an alkaline metal, so hopefully you remember that has to be a +1. Well, oxygen, we have a rule for that. This is not peroxide. This is not O2, 2 negative. This is just oxygen. So we have a rule for that. That's going to be -2. So the crisscross method, once again, you take this number and put it down here for the subscript. You take that number, the absolute value, and put it down there. So lithium 2, oxygen 1, which we don't write the 1. We're just going to put lithium 2, oxygen. That's the way that would combine. Again, hopefully you saw how we use the oxidation rules. Lithium has an oxidation number of +1. Oxygen has an oxidation number of -2. We know that because of our rules. Just do the little crisscross method and you get your answer, lithium 2 oxide, or lithium 2O for this particular lesson. So it's a very fascinating concept, not super hard, but very interesting. You got to know your rules, though. That's very, very important. All right, just a few more slides here. Some atoms can have more than one oxidation number. The transitional metals often do, nitrogen does. So you just need to remember that a lot of them can have multiple oxidation numbers. There are some exceptions to this, and we've already talked about those exceptions. Those are the rules that we have. Now here's a chart that you guys have in the textbook. I believe it is on page number 194. I will give you a copy of this chart. I do not expect you to memorize this. It would be overwhelming for many of you. However, I will point out that the ones that you guys see in yellow, the boxes that are in yellow, those are the ones that the textbook is going to use quite a bit. So here you can see there's several different options, but if you look at column 1, again, this is just interesting. Column 1, with the exception of hydrogen, all have a +1 oxidation number. They're all in column 1. Column 2, all have a +2 oxidation number, the alkaline earth metals. Fluorine, we've already talked about fluorine here. That has an oxidation number of -1. And then if you look at this column, the halogens, you'll notice they all have at least a -1 in there. You can see, obviously, fluorine does, chlorine does right there, bromine does there, iodine does there, and astatine does right here. So those are the halogens. But again, pick any of the one that has multiple states. Let's say I were to just use as an example iron. Iron is right here, Fe. Notice it has 2 oxidation states. It has +3 and +2. Now we're going to talk about this when we get the nomenclature. It is important to know which one is used in the molecule, but this is just a way you can know what's the possible combination. And let me say this, using this chart here, you can see why the formula of that the oxidation number has to equal 0 is so important. And this is also where the crisscross method comes into play. I'll just pick one as an example here. Let's say I was dealing with cobalt, which is CO, which is right here, and maybe I was dealing with I don't know, let's do chlorine. Okay. Well, we have a couple of things we have to consider and we have to be careful of. The easiest way to do this is to say, okay, cobalt can have, this is probably not the best example, but we'll go with it anyways. Cobalt could be +3 or +2. So cobalt could be +3 or +2. I do know chlorine. Chlorine has to be -1. The way I know chlorine has to be -1 because it's more electronegative than cobalt. The nonmetals, all the stuff on this side, are more electronegative than all of the metals. Okay, got to remember that. So possibly I could put a 2 here, or I could put a 3 here, which is actually kind of fascinating. But let's just say I'm going to use the 2. Well, that 2 is going to come down here, and this 1 is going to come down here. So cobalt, CO, Cl2 is a possible combination. Now some of you ask, well, what about the +3? Why'd you just get rid of that? Well, it's possible that I could actually have CO, Cl3, and both of those compounds would actually exist. So that's kind of interesting. But we're going to use this quite a bit. This chart is extremely important, so you want to be very familiar with it, but we'll practice with it quite a bit. Okay, polyatomic ions are covalently bonded groups of atoms that carry charges. So you can have a polyatomic ion. Poly means many, so their charges are going to change and be different. And we're going to talk about this extensively in just a couple of examples later in this chapter. Polyatomic ions survive most chemical reactions without breaking up. So if you had a polyatomic ion, like an example would be PO3 phosphate. PO3, I believe, is a -2 charge. So this is a polyatomic ion because the whole molecule is actually an ion. The O3 are all under the 2 negatives. So we'll talk about what this means later when we get to oxidation, some other oxidation number concepts, and also the molecular bonding and naming of compounds and stuff like that. But what it's saying is, I'm just going to make something up here. If I had H2O and I added it to phosphate in the reaction, when I put those two things together, more than likely the phosphorus and the oxygen are going to stay together. Now the subscripts may change, but the elements themselves stay together. So that's kind of the idea behind this. You really don't need to know it that much for this particular concept, but this will definitely come into play in just a couple of pages in this chapter. A couple more and kind of applies to this rule right here, rule number 5. The oxidation number of all atoms in a polyatomic ion add up to its charge. Use the charge of the ion just like you would use for oxidation numbers, and this technique can be used for polyatomic compounds. So here's the example that it's talking about. So if I have PO3 and that charge is a -2, now do keep in mind it will not be written in parentheses. It'll be written like this. What it's saying is you have phosphorus, you have oxygen, and we have oxidation numbers, but the sum of the oxidation numbers on this ion are not equal to 0, but they're equal to the charge, -2. So here's how I apply my rules. I have a rule for oxygen. I do not have a rule for phosphorus. So let's go with the rule I know. Oxygen is going to be -2, but if you guys notice, you have 3 of them. You have 3 oxygen, so that's going to give us a total of -6. Well, what plus -6 is equal to -2? Well, obviously that is 4. So the oxidation number of phosphorus is +4, and the oxidation number of oxygen was -2, as you guys recall, but we have 3 of them. So -2 times 3 is -6. Remember, previous problems, the sum of the oxidation number had to equal 0. And in the vast majority of the times that's the case. But when you have a polyatomic ion, it's always going to equal the charge. The sum is going to be equal to the charge, not to 0. That's the only tricky rule, in my opinion, that you got to remember. So make sure you remember that. Well, guys, that's it. We finished section A in this chapter 8. It's not a super difficult lesson. I know it may seem a little weird. Many of you probably remember some of this from physical science. But even if you didn't, if you remember your rules, you're going to do fantastic on the application of this section. I'm not going to give you a test or a quiz on the rules and ask you what's rule number 4 or what's the exception to rule number 3. I'm not going to do any of that. But you have to master the rules in order to be able to correctly get the application correct. But we're going to practice some of these tomorrow when I get back, and hopefully you guys will be able to pick up quickly on this so that we can move on into the nomenclature section of Chapter 8. Hope you guys have a fantastic day. Thank you for listening. I know it's kind of tough at times to listen to the presentation presented this way, but I thought it was the best I could do in order to make sure we don't lose track and lose ground in this particular class. But have a fantastic day, and look forward to seeing you guys tomorrow.